Let's work on even or odd functions. So reminder, this is all about symmetry of a function, whether or not it's an even function, it is symmetric over the y-axis. If it is an odd function, it is symmetric over the origin. So let's work on number one. I want to show that g of x, which is x cubed plus 1 over x, is odd. So notice that in this definition of the function, I'm taking x and I'm cubing it. Cubing, that's an odd thing. I'm multiplying it by itself 3 times. Here I'm taking 1 over it, so that's also an odd. So all of the powers of x are odd here. Right here it's a power of 3. Here it's a power of -1. But all of my powers of x are odd, so I want to show that the definition of odd is satisfied. That is, I want to show that g does to minus x the opposite of what it does to positive x. Right, if here I have an x value and g takes it up to this y value, so this is g of x, then over here at minus x, it should do the opposite. It should go down here at minus g of x. Right, we get this symmetry over the origin. Now, so this is what I want to show. So let's show that this, before we graph it, let's show algebraically that this is an odd function by showing that the definition is met. So let's start with g of minus x. So if g does this to the x values, then it will do the same thing to minus x. It will take its input, which in this case is minus x, it'll cube it, and it'll add 1 over the input, minus x. Right, that's just my function g evaluated at minus x, and then hopefully we end up with our right-hand side minus g of x. So this cube right here, I can distribute it to the -1 and the x separately because powers can distribute across multiplication. So -1 cubed and x cubed. This term right here, instead of saying plus 1 over minus x, we could just say minus 1 over x. Now, -1 cubed, -1 times -1 is a 1, but because it happens an odd number of times, when I multiply by -1 again, I end up with a negative out there, and then I have this x cubed. Oops. There we go. And let's pull out a negative because I know that in my definition, what I'm trying to show, I've got that negative right there. So if I pull out a negative, I'm left with x cubed from that term and a plus 1 over x from that term. Right? In other words, we just use the distributive law backwards. If you go from this line back up to that line by distributing this negative sign, you should get back up to there. But this is exactly what we wanted to show, right? This is minus, and then what's in this parentheses? That's my original g of x function. So we've shown that g of minus x is equal to minus g of x, which is the definition of oddness. Therefore, g is an odd function. And notice that we didn't have to specify what x was. This is going to be true for all x values that's inside the domain of g. So if we were to graph this, let's look at a few points. -1, -2, -3, 1, 2, 3. Now, g of -3, by my definition, that it's odd, should be the same thing as minus g of 3. So I can use that. Right, if I plug -3 into this function, I get minus 27 and 1/3. So over here at -3, the function returns minus 27 and 1/3, which means over here at +3, it's going to return positive 27 and 1/3. If we look at g at 2, this is going to return a 8.5. So over here at 2, my function is 8.5. Which means by my definition of odd, the function at -2 should be minus 8.5. All right, and we'll proceed in this manner. We can evaluate the function at -1, and g at -1 gives you a -2. So my y-axis is not to scale, which means that my function at 1 is a +2. In fact, let me move this point. 2 is a little bit closer to my x-axis. There. Okay. Just get a better idea of what this graph is going to do. I know that my domain, if I go back to my definition of G, right, I'm taking x cubed, which could be anything, and then I'm adding 1 over x. So I'm not allowed to get close to 0. Or rather, I can get close to 0. I can't plug in 0. If I try to get close to 0, if I look at G at 0.5, I get 2 and 1/8. So at 0.5, I get a little bit above my 2 there, which means at minus 0.5, I should get -2 and 1/8. So the shape that we're going to get is something like this. Right, but notice that is an odd function. In fact, if I can clear this up, and if we don't care about scaling our x-axis and our y-axis correctly, and we just want a general idea of what the shape of the graph is going to look like, it's going to look something like this. Now, notice that's odd, right? This is symmetric over the origin. I could take this part of my graph and reflect it over my y-axis, and then reflect it over my x-axis. And I get exactly that second part of my graph, right? It's the definition of odd. This x value gets mapped up here, so its negative gets mapped down there. Okay, let's work on number 2. Number 2, we want to show that a function is even, x to the 4th minus absolute value of x. So notice this is going to be an even function because what's our definition of even? The function at minus x should return the same thing as the function at x. So in other words, if we're over here at x and our function gets mapped up to this point, then minus x should also get mapped up to that same thing, to that same y value. So I'm symmetric over my y-axis here. All right. So let's show that this definition is satisfied. F at minus x is minus x to the 4th plus absolute value of minus x. Now, minus x to the 4th will be the same thing as x to the 4th. Right, for the same reason, I can distribute that 4 to the -1 and the x separately, -1 to the 4th, the negatives cancel and you're left with a positive, right? You're taking a negative to an even power, so it's guaranteed to be positive. In this term, the absolute value, by definition, returns the magnitude of the value, or the absolute value. So the second term becomes just plus absolute value of x. Oh, wait a minute. No, I made a mistake. It's supposed to be x to the 4th minus absolute value of x. So right here, I have a minus sign. So I have minus absolute value of x. Right, this is my function. So I showed that this definition is satisfied. I started with f at minus x, and I have the same thing as f of x. So if we were to graph this function, I won't go through the points this time, but you're going to end up with a shape that looks like this. So poor art skills, but that's symmetric over your y-axis. It's an even function. Whatever the function does at this point, x, it'll do the same thing at this point, minus x.